We've been partying. Right, I don't know why I'm lowering that. There's a big note that says the right-hand projector doesn't work. Now, to me, that would be the right-hand projector. They're clearly not the other one. So, anyway, I've confused the issue. Right, to business. Now that's stopped roaring away. We started to look last time at some of the chemical processes associated with mineral alteration, yeah? And that is the slide where we finished off. And the reason I stopped a couple of minutes early is because this diagram is next up. And what this is a sequence of little cartoons which illustrate the sorts of processes which go on and lead to structural and chemical alteration. So we've got a hypothetical feldspar. So we start here, diagram 1. So feldspars are, in this case it's a sodium form, so it's a sodium aluminosilicate. Our tetrahedra comprise either silicon or aluminium centered tetrahedra, and we balance the charge we balance the charge shortage that we get from having aluminium in the centre of the tetrahedra by putting extra positive charge, in this case in the form of sodium ions, within the lattice. So this broken line, if you like, marks the boundary between the solid mineral crystal and an aqueous solution phase. And this sequence of reactions, first, second, third, fourth, illustrates the steps in the alteration, the structural and chemical alteration and partial dissolution of this feldspar. So the first thing that we can do is, at the surface of the mineral, you can have some net negative charge, okay? Because these are oxygen corners of a tetrahedron. They're on the surface, so they're one bond short and they carry a net negative charge. And you can protonate those, so that you can take protons out of solution so that they will become OHs. That's the first thing you can do. The second thing you can do is you can actually exchange metal ions near the surface, like this sodium, for hydrogen. So that sodium will drift out into the solution and will be replaced by a hydrogen. And when those steps are complete, we've moved from that to that. So we've lost the sodium that was in there, it's now drifted off into the solution. And we're protonating a number of the oxygens at the corners of this tetrahedron here. If we can repeat the sodium exchange process, so we put a proton in there and we let that sodium drift out as well, that will then protonate the last of these corners of this particular tetrahedron. If you like, it's a pair of scissors, and what we've done is we've cut the last bond that holds this tetrahedron into the structure of the feldspar. So what drifts off into solution then, as well as the sodium ion, which isn't shown here, is this species, which is H4 SiO4, silicic acid, which we talked about. So these processes, so this is trying to illustrate at a near molecular scale the processes which go on and lead to the chemical alteration of minerals like feldspars and the dissolution and modification of their structures. And we'll return to the consequences of that in a few minutes. I mentioned also that redox reactions have an important influence on near-surface geochemical behaviour. And if we think about the elements that are present in reasonable quantity near the surface, then carbon's an obvious one, nitrogen, sulphur, oxygen, iron and manganese. And when you look at the redox processes that actually occur, then carbon, nitrogen, oxygen, sulphur are intimately linked in biological transformations. So, we have things like respiration, photosynthesis, and particularly when we come on to anaerobic processes, we'll find that nitrogen species and sulphur species are particularly important there. So if we just look at those elements, the sorts of things that you can find are, in some circumstances you can find sulfate, in others you can find elemental sulfur, in others you can find sulfide. And indeed there are other sulfur species like thiosulfate also encountered. Similarly, the important nitrogen species are nitrate, dinitrogen and ammonium. So we've got quite significant redox changes between, if you like, formerly sulfur plus 6 and sulfur minus 2. Or here, nitrogen formerly plus 5 and nitrogen formerly minus 3. We can also see that the metallic species, iron 3 and iron 2, manganese 4 and manganese 2. And the reason I'm emphasising this group of elements is because there's often, relatively speaking, quite a lot of them present. So, by driving redox change in these species, you will actually, or you can actually, change the behaviour of the whole system. So here's a simple example. Let's compare selenide, selenate oxidation, selenium being a trace element, and sulfide, sulfate oxidation. So two directly analogous chemical processes. If you take a hypothetical sediment with those, so that mass of it, that moisture content, that pH, and that selenium content. The ppm is a microgram per gram, or a milligram per kilogram, or a gram per ton, so not a lot. Then, but that selenium is usually present because it's a trace element at part per million concentrations. So we have a simple equation for the oxidation of selenide to selenate, which is accompanied by the release of lots of protons. So you would get a substantial release of protons into solution accompanying any of these oxidation reactions. But because we only have a tiny amount of selenium present, 1 part per million, the total amount of hydrogen released in our hypothetical sediment is only 10 to the minus 4 of a mole. And even if that system were not buffered with respect to pH, that would give you something like a minus 3 units pH change. The reality, of course, is that natural systems are really quite well buffered. There are lots of places that protons get soaked up again. And actually, if you oxidize that quantity of selenium from selenide to selenate, you'll see no significant perturbation of the pH at all. But let's take exactly the same process at a plausible sulfur concentration with our sulfur present as sulfide. Here we're looking at 1% sulfur content. So 1% is 10,000 parts per million. So that is a much higher mass concentration than we have for the selenium example. Allow the same reaction to occur. We get 8 protons released for every mole of sulfide oxidized. That will give us a whole mole of protons released in our hypothetical volume of sediment, and a much, much larger, 4 orders of magnitude larger change in pH, which is probably beyond the buffer capacity of a natural system. And so this just is an illustration of my point, that if you're messing around with trace elements, it matters because you're concerned about the trace element's behaviour, but that's all. If you're messing around with the major elements, then actually that will have, or can have, consequences for the whole system. Okay, I said we'd look at clay minerals again. So, they are formed by the weathering of aluminosilicates. We'll look in detail in a minute at what they actually are. But as a family, they have some common characteristics. They're hydrous, so they have a lot of water and hydroxide in their structures. And they're actually made up of layers, so they have this sort of sheet structure. They're sandwich minerals. And that takes us into the classification of the clays, because we can start to understand the tremendous diversity of the clay minerals on the basis of the composition of the sheets that make them up and the sequence with the stacking structure. And when you look across the family of clay minerals, we actually have 2 basic types of sheets that make them up. So there are tetrahedral sheets, so that's sheets of linked SiO4 4- tetrahedra, and then there are also octahedral sheets. So those are again oxide sheets with octahedra of oxygen atoms, and in the centre of those octahedra either aluminium or magnesium. I think this battery is not doing it any good. I'll knock the lights down and see if we get on a bit better. So the octahedral sheets are linked octahedra, edge sharing, with aluminiums or magnesiums in the middle, and oxide or hydroxide at the apices of the octahedra. So those are our 2 basic structural units. If you think about it for a second, aluminium is Al3+, trivalent. Magnesium is Mg2+, divalent. So if you have an array of oxygen octahedra and you neutralise the negative charge from the oxygens by using aluminiums, you will only need 2/3 as many aluminiums as you would magnesiums, because each aluminium neutralises 3 units of negative charge. So a pure aluminium-based octahedral sheet would only have 2/3 of the octahedra with a metal ion in, because that would give it electrical neutrality. If you're neutralising that charge or compensating that charge with magnesium, because it's divalent, then you would need to put an Mg2+ in all of your octahedra to neutralise the charge. And this gives you a bit of nomenclature. So the aluminium-based sheet with 2/3 of the octahedra filled is sometimes referred to as being dioctahedral, in contrast to the magnesium-based sheet with all the octahedra filled, which is referred to as being trioctahedral. And they're also sometimes referred to by the names of the related minerals. So if you have a hydrous aluminium oxide, that is the mineral, my battery's finally given up, that is the mineral gibbsite. So you sometimes see aluminium sheets referred to as gibbsite sheets. And similarly, hydrated magnesium oxide is the mineral brucite. So the magnesium sheets are sometimes referred to as brucite sheets. And what we find, depending on the layer sequence, sometimes the layers are stuck quite well together, and sometimes they're stuck only fairly weakly together, and it's possible for the layers to drift apart, and for example to put a layer of water molecules or small metal ions in between the layers. So those clay minerals will swell and shrink depending on how well hydrated they are. If there's a lot of water around, the layers move apart. If there's not so much water around, then the water drifts out from the interlayer spaces and they come back together. And that actually is one way you can identify the clay mineral you're dealing with. You can do X-ray diffraction of the hydrated mineral, and the D-spacing will be big. You can do X-ray diffraction of the dehydrated mineral, and the D-spacing will be small. You can also pre-treat them with things like ethylene glycol and look at what that does, because some of them can take fairly big organic molecules. So just by conditioning the interlayers and looking at how that changes the D-spacing is one way of identifying clay minerals, but that's probably a bit much detail for you. The other thing that clay minerals have, particularly the expanding clays, the ones that can move the layers apart, is they have a very high, what's called a cation exchange capacity. Now we've got these layers, they've got charge compensating cations in the middle of the octahedra or the tetrahedra. You've got hydroxides, you've got oxides, sometimes you've got vacancies, sometimes you've got substitution of cations. You very often you generally don't get perfect charge compensation within a layer. So what that means is that your sandwich, as you stack the layers up, will have either a charge deficit or a charge excess. And one way of neutralizing that is by putting extra cations, or usually cations, into the interlayers. So, for example, you have a net negative charge from the two layers above and below, but you put a few, I don't know, sodiums or potassiums into the interlayer, and that allows you to compensate for that overall negative charge excess. And because those cations are not held in the clay mineral structure, they can drift in, they can drift out, they're what's called exchangeable. We'll come on to a story about exchangeable cations later on. And the quantity of cations that are exchangeable in that way can be measured, and that is called the cation exchange capacity of the clay. So it's a bit like a sponge for cations from solution. It can take them up and it can let them go again easily. And those exchangeable cations are really very important in a number of different contexts, and we'll look at one in a minute. So what else can happen? I've mentioned that the layers are rarely stoichiometric. Rarely, probably never stoichiometric. So you can get substitution and replacement of ions within individual layers. So you might have a generally magnesium layer, but with a few iron 2s in it, for example. Or, okay, the example I'm giving here is, right, an aluminium-based layer, so that's gibbsite, 2/3 of the octahedra ideally occupied, 1/3 of the octahedra vacant, but you could replace some of the aluminiums by divalent ions such as iron 2 or magnesium. And at that point, you're getting a further charge imbalance because you're replacing trivalent aluminium by divalent iron or magnesium, and you need to compensate that. And there are a number of different signs. I talked about the interlayers already, but as well as that, you can put compensating cations round the edge of the sheet, or you can put them onto the surface of the sheet. And if you think about it, I'm talking about putting things into interlayers, I'm talking about putting them on binding sites, on edges of sheets, I'm talking about putting them on surfaces of crystallites. Now those are quite specific sites. They can be quite small, they can have specific stereochemical requirements. So cations are not all equally useful in binding to these sites. So for example, sodium and potassium are relatively small and will bind in one way. Cesium is, well, rubidium and cesium are rather bigger and they bind in a different way. So particularly the size of a cation is really quite an important control on how it actually participates in these ion exchange processes. So here we have an idealized description of the principal clay minerals. We'll look at some pictures in a minute. So the simplest one, the one we already met, is the mineral kaolinite. And what that consists of is a sequence of one octahedral layer with one tetrahedral layer stuck to it, then another octahedral, then another tetrahedral, and so on. The idealized formula for kaolinite is that Al4Si4O10OH8. The octahedral sheet, pretty obvious from the idealized formula, is an aluminium-based or dioctahedral sheet. And because you've got this sequence of octahedral, tetrahedral, and they're all stuck firmly together, kaolinite is not an expanding clay. So you can't get things into the interlayers of kaolinite, and that's where a lot of the cation exchange capacity lives. Therefore, kaolinite is an example of a clay which has a low cation exchange capacity. Do you know what equivalents are? It's a sort of Stone Age chemical unit. So, yes? No? Okay. Somebody says yes, everyone else is denying all knowledge. Do I need to explain equivalents? Let me take a moment.
Yeah.
Right, okay, I will. There's clearly uncertainty about equivalents. I will explain them. An equivalent is essentially a measure of quantity that's used in chemistry, but it takes account of charge. So, for example, you're thinking about moles of charge. So 1 mole of sodium, being monovalent, would be 1 equivalent of sodium. 1 mole of calcium, being divalent, would be 2 equivalents. 1 mole of aluminium, being trivalent, would be 3 equivalents. So just think of equivalents as being moles of charge. And the units that are normally used to measure cation exchange capacity are milliequivalents, so thousandths of equivalents, per 100 grams of solid. So kaolinite at, say, 10 milliequivalents per 100 grams. What that means is its ion exchange capacity is 10 millimoles of positive charge in every 100 grams of kaolinite. That's all that means. Let's look at the next example, montmorillonite. So that's an example of an expanding clay. And here we have a more complex repeat sequence. We have a tetrahedral, octahedral, tetrahedral sequence. So 3 layers stuck together, and then you have a gap, and then tetrahedral, octahedral, tetrahedral repeats. And it's that gap between the 3-layer slices which gives montmorillonite its ability to expand. The ideal formula's there, and cation exchange capacity reflects the fact that montmorillonite's an expanding clay. It's around about 100 milliequivalents per 100 grams is pretty typical for an expanding clay. So that's sort of idealised montmorillonite. Illite is a bit of a funny one. It's related in some ways to the montmorillonite structure. You still have the tetrahedral, octahedral, tetrahedral sequence, but you have aluminium silicon substitution, which leads to charge imbalance, which is compensated by a bit of potassium, and the end result of all that is to make the layers much less easy to move apart. So illite tends to expand to a lesser extent. It still does expand to a degree, and its cation exchange capacity is consequently somewhat lower. Vermiculite is again a three-layer clay, tetrahedral, octahedral, tetrahedral, but this time with a magnesium-based octahedral layer, giving you that ideal composition. And it's essentially the magnesium analogue of montmorillonite, and typified by really quite a high cation exchange capacity. And then chlorite, which is a sort of rubbish mineral, really, it's a horrible thing. That's tetrahedral, octahedral, tetrahedral, isolated octahedral layer. Then repeat tetrahedral, octahedral, tetrahedral, and so on. And it tends to be very much a magnesium-based mineral, hence that formula. A few notes. I said they're complicated things. Montmorillonite, you can get magnesium ion substitution for aluminium. In illite, you get this aluminium silicon substitution and the charge imbalance. You can get iron magnesium substitution in vermiculite, and you can get aluminium silicon substitution in the tetrahedral layer. And chlorite, as I said, is compositionally very variable. So take that previous slide very much as the ideal of clay minerals, which you will never ever encounter. Here are some pictures which try and illustrate these structures a bit better. I'll have to point with the mouse, I'm afraid. So here is kaolinite. These diagrams, the ball and stick ones, are a bit easier to see. So here we have an octahedral layer. Sticking to it, we have a tetrahedral layer, and then that unit repeats, octahedral, tetrahedral. And the interactions between these tetrahedra and these octahedra are relatively strong. Therefore, you can't put cations into this gap in the middle. If we look at vermiculite, and we've seen an example of it, expanding clay, then that's based around the tetrahedral, octahedral, tetrahedral, three layers stuck together sequence. Let me curse it. So tetrahedral, octahedral, tetrahedral, and then it repeats, tetrahedral, octahedral, tetrahedral. And here we've got much weaker interaction between this group of layers and this group of layers, and we can put all sorts of things into this gap. So water, calcium, magnesium, sodium, ammonium, they can all drift into this gap. And that's why it's an expanding clay. You put stuff in there, the layers move apart. You take stuff out, the layers come back together. Chlorite, purely as an example, okay, we have tetrahedral, octahedral, tetrahedral, isolated layer of octahedra, tetrahedral, octahedral, tetrahedral, and repeating. And because we have the isolated octahedral layer in here, we have a lesser ability to expand, and therefore we have a somewhat lower cation exchange capacity. Right. I'm going to spend a little bit of time talking about the specifics of ion exchange on illite and related minerals. And this is very much a cartoon. So illite has some ability to expand, and therefore some ability to take in hydrated ions into at least the edges of the crystallites. So the picture we have in our mind when we're thinking about illites is that these are, if you like, the aluminosilicate layers, and particularly at the edges you can get equated ions and water coming in and opening them up. So if you think of it as being like a sandwich, what you're doing is you're peeling apart the bread at the edge of the sandwich and putting cations in there. And at the edge of the sandwich, those cations tend to be hydrated, and therefore the gap is quite large. So, but as you go into the interior, what you tend to find is that those cations have become dehydrated, therefore they're much smaller, and the layers have become pulled together. So if we just look at this middle sequence here, this is collapsed. These are in what's sometimes called a wedge zone because it's wedge-shaped. And then at the edge, at the perimeter, you have the hydrated ions still. And that turns out to be important because you can see a sequence of events. Initially you get diffusion of hydrated ions into the wedge zones. And I'm going to talk particularly about the ion cesium here, which is relatively weakly hydrated. So it tends to let go of its water. As a result, in the wedge zone, you've got a relatively dilute solution. And you've got, compared with the soil solution outside, you've actually got an osmotic pressure which pulls free water out from the clay interlayer. So the water not only comes off the cesium, but it actually moves out of the interlayer. And therefore, the interlayer starts to collapse because you've not got enough water in there to hold it apart. And you get this sequence as we go from top to bottom of the wedge zone starting to collapse and the cesium ions becoming trapped within it. And sometimes you can get this sort of thing going on where the edge collapses and just pinches off the mineral. So you still have an expanded bit in the interior, but that water has nowhere to go. And why is all this important? It's very important when you start to look at a number of key plant nutrients, particularly potassium in soils, and also an ion that's important in the context of radioactive contamination, cesium. Because cesium is one of the predominant fission products. And the oolitic clays that we've talked about are the most important ones. And I've just talked you through at some length the process by which cesium can come into an interlayer, will dehydrate, the water comes out, and then the clay will collapse and trap the cesium. So you're far too young to remember Chernobyl, I guess. 1986, none of you born, were you? No. It was my first nuclear reactor accident, memorable for collecting some rain. It came in a holiday weekend in April, and it's memorable for where I worked at the time. They had a little weather station with a rain gauge, and we came in on after the holiday weekend. We took the water from the rain gauge, we put it on the detector, and it is one of the hottest things I have ever seen. It was absolutely screaming, and then all hell let loose, and I spent a week sleeping on the lab floor while I was doing plutonium separations. So you do a bit of separation chemistry, a couple of hours kip in a sleeping bag on the floor. Next step in the separation, another couple of hours kip. Week of that, I was knackered. It was not good. So reactor accidents are just very bad. We don't want them. And because this happened much closer to the UK, we saw a lot and was significant deposition of radioactivity on the UK. It was far more significant than last year's, or 2011's Fukushima accident, because that was far enough away that basically the UK didn't really care that much. Which is good, because sleeping on lab floors at my age is really bad. Okay, so in April 1986, the Russians screwed up big style and blew the roof off a nuclear reactor, which is generally a bad plan. And they set what was inside on fire, which is also a bad plan. So, if you really want to screw up, they did it. And they cooked off large quantities of radioactivity, including the radioisotopes cesium-137 and cesium-134. And 134 is pretty much gone now because that has a 2-year half-life. But 137 has a 30-year half-life, and it's still around. And it's the cesium, actually, from Fukushima that's causing the Japanese these long-term problems about how can they reoccupy settlements they've evacuated and so on. And because it was a bank holiday weekend in the UK, it inevitably rained. What you had was you had this contaminated air mass moving around, and where it coincided with heavy rainfall, the rain washed the radioactivity out of the air and deposited it on the ground. And we'll look at some maps and things in a minute. Now, mostly in the UK, the predominant cation in soil solution is actually potassium. And potassium is big enough and weakly hydrated enough that it will cause this clay collapse. In terms of mass concentrations of cesium, you're talking probably 10 to the minus 15, 10 to the minus 18 molar. So you don't really have enough cesium for it to have a chemical effect. And what it gets caught up in, basically, is the potassium chemistry of the soil, because they're close enough chemical analogues. So if you've got a background potassium concentration and you add a tiny bit by mass of cesium, then because the potassium is triggering clay collapse and fixation, the cesium will be fixed as well. And once the cesium is fixed, it's just going to sit in the clay and decay away, and nobody really cares. The problem we have in the UK is we have quite a lot of upland soil. And in these, they're very potassium poor. And the dominant soil solution cation is actually hydrogen. They're quite acidic. And hydrogen and cesium are really not good chemical analogues. Hydrogen does not induce collapse in the interlayers. There isn't enough mass of cesium to induce collapse. And therefore, what happens is the cesium may drift in, but it can drift out again. You don't get the collapse. The cesium simply recycles. So it goes from soil into the grass, the sheep eats the grass, the sheep becomes radioactive slightly. And the bit that doesn't get taken up into the sheep's tissues comes out the other end of the sheep and recycles back into the soil. So here are some pictures. Right, I did tell you they made a mess of their nuclear reactor. That's it. There's some really interesting imagery of a Russian military helicopter, some guy leaning out the door, sort of hovering over that. The guy's got a radiation monitor, and it's subtitled, and you can tell the guy with the monitor's agitated because he's yelling at the pilot, and the subtitles say something like, "Go higher, please go higher." And I watched that once with a Russian speaker, and he said those were not the words the man was using. He was considerably more stressed than that. So basically they blew the lid off, they set fire to the remains of the reactor, so this smoke in the middle is actually quite highly contaminated with all sorts of horrors. Because it was an operating reactor, it was full of fresh fission products. Where is it? It's there. So it's still quite a long way from the UK. Ah, that went wrong. We've gone 100 slides on. I think we might wind the clock back a bit. That looks more helpful. Yeah, okay. So, right, so that's what it looked like some time after, when they'd actually put the fire out. And that's not what a nuclear reactor's meant to look like. This is a cross-section, so the reactor itself sits in here. And what's interesting, well, there's all sorts of interesting things if you're a sad reactor obsessive like me, is that the whole thing set on fire, it overheated, and actually a whole bunch of the fuel melted. And underneath the reactor, here,
you've got a whole bunch of inspection chambers, and it's all built on sand to act as a bit of a cushion in case you get little earth tremors. And this molten reactor fuel chewed its way down through the bottom of the reactor, met the sand, chewed its way through that, and started to pour around like a sort of radioactive lava into the inspection and service tunnels underneath. And this is what came out. So up here there's a sort of inspection hatch, and this sort of thick goo poured out from the tunnel. So that's hot as hell. And they sampled it by getting a soldier to stand about 20 yards away and shoot bits off it, and then sent a little remote controlled vehicle to pick the little fragments up, because you really don't want to go close to that. It's very bad. So it's I've done it again. Sorry. I'm getting carried away. Too excited by reactor accidents. Okay, right, now we'll take care about what button I press. Okay, so here's a sequence. Late April 1986. The origin of the plume is here. It drifted westwards initially. 28th of April, it had gone further westwards and then got caught in an air mass moving it northeast. But it was over Sweden, and that was the first indication something was wrong, because again, you probably don't remember Cold War and stuff, really, do you, either? The Russians didn't really talk very much to Western Europe, and would deny there ever having been a reactor accident. And the first indication that something was seriously wrong was when a Swedish nuclear power station found all hell letting loose with the alarms. And at that point, the Russians had to say, actually, guys, we have made a mess of this. And then so the air mass starts. The contamination gets swept up in the air mass, distributed fairly well around Central and Eastern Europe, and then over the bank holiday weekend starts to come much more westwards. And so this is the period when it starts to come across the UK. This is just a very rough estimate of how much came out when. Blow the roof off and set it on fire, you get quite a lot out. And then it sort of calmed itself down for getting on for a week, and then it started to speed up again. They built up temperature for a bunch of reasons, so the release rate went up again, and finally, about 10 days after the accident, they seemed to get a grip on it, and the release rate fell right down. So it was released over quite a prolonged period. Oh. I'm just obsessed with that key for some reason, and it's really not helpful. Okay. Do not touch the end button. Do not touch the end button. Okay, so focusing in on a bit of northwest England. This is a very simplified soils map, and it's based on the content and type of clay present in the different soils. And basically, the darker the colour, the less able to immobilize cesium the soils are. This is a map of deposition, and you'll see that it's focused very much on the central and western or southwestern part of the Lake District. In other words, fairly well coincides with a chunk of soils that aren't too hot on immobilizing cesium. Yes, I managed. Right. And quite quickly after the event, people realised that a lot of it is upland, it's sheep grazing areas, and people realised that actually the sheep were relatively contaminated. And what was then called MAF, Ministry of Agriculture, Fisheries and Foods, imposed restrictions on moving and selling sheep from the uplands without first monitoring them. And this is the outline of the restricted area which was put in place in 1986. And I would put it to you that the shape of the restricted area pretty much matches the vulnerable soils overlain by the high deposition. So where you had vulnerable soil and you have high deposition, then you have long-running sheep problems. And indeed, it's only in the last year or two that the last of the restrictions have been lifted from that part of the country. Yeah, let's stop there. Okay, so hope you got something out of that, and I'll see you next week.